All right, in this problem, what we're doing is we're going to consider 5 different metrics. Really all metric is kind of a notion of distance. So this is kind of our standard notion of distance when we talk about the real numbers. Like if we have 2 different real numbers, x and y, and we want to know how far apart they are, we subtract them and take the absolute value of that number. The distance between 7 and 12 is the absolute value of 7 minus 12. The absolute value of negative 5 is just 5. But there's other notions of distance that can make sense in a given context, or just that make sense theoretically. As long as the distance between a point and itself is 0, the distance between any 2 distinct points is greater than 0, the distance between x and y is the same as the distance between y and x, and the triangle inequality holds, that is, the distance between 2 points is no further than the sum of the distance from the first point to some other point, and from that other point to your second point. As long as we satisfy these 4 criteria, we have a perfectly legitimate metric. Not a horrible idea to convince yourself that each of these different functions does in fact define a metric, in other words, satisfies these 4 criteria, but you don't have to do that because they kind of tell you that in the problem. We're not trying to figure out if these things are metrics. What we're trying to figure out is which of these things, when used as a notion of distance with the real numbers, defines a complete metric space. What it means for a metric space to be complete is just if every Cauchy sequence of points converges to a point in that space. So we understand what a metric is, which allows us to define a metric space. We understand what a complete metric space is. The only problem is within this definition of a complete metric space, we reference these things called Cauchy sequences. So we got some sequence a sub n, and the idea is it's Cauchy if for any epsilon greater than 0, there exists some number n so that the distance between maybe a n1 and a n2 is less than epsilon for all n1 and n2 that are greater than or equal to capital N. You give me some really small positive epsilon, I'll tell you a point in the sequence so that any terms further on in the sequence are within that epsilon of each other. So what this question is asking is, if I have such a sequence with these various notions of distance, am I guaranteed that the limit of this sequence will fall within this space? And you might be like, wait, wouldn't that always happen? Well, not really. If the space in question has holes in it, either within the space or kind of at the endpoints, then you can absolutely define a sequence so that all the terms of the sequence fall within that space, but the limit does not. So for example, if the space that I'm talking about is the rational numbers, and I use my kind of standard notion of distance given up here in part A, this will not be complete. And informally, the reason why is because the rational numbers have a bunch of holes in them. I can define a sequence of rational numbers, specifically a Cauchy sequence of rational numbers, that converge to an irrational number. For example, if the first number of my sequence is 3, and the next one is 3.1, and the next one is 3.14, and the next one is 3.141, and then 3.1415. And I continue to define these terms in the sequence, where a sub n is the, n minus 1 decimal place approximation to pi. Clearly, these are all rational numbers, right? I can write them as terminating decimals, but clearly they converge to pi, which is an irrational number, so it's not in this space. This sequence is Cauchy because you can pick whatever epsilon you want. Think, 0.0001, sure. And I can find some point, right here, so that any terms after this point in the sequence will be within this amount of each other. So this Cauchy sequence in this metric space would be a counterexample showing us that this metric space is not complete. Maybe one more counterexample. We'll define the set R to be equal to the set of all real numbers that are between maybe 0 and 1. Maybe we'll include the endpoint of 1, sure. In interval notation, we're just talking about all the numbers from 0 to 1, not including 0, including 1. If we consider the metric space R with, again, our standard notion of distance, we can show that this is not complete. To do so, we need to find a Cauchy sequence where all the numbers in this sequence fall within R, but the limit does not. Can you think of such a sequence? The classic example is to let a sub n be equal to 1 divided by n. All right, so my sequence is 1, 1/2, 1/3, and so on. Clearly, all these numbers fall in this space. Clearly, maybe this sequence is Cauchy, something you'd want to convince yourself of. But the limit as n approaches infinity of this sequence is equal to 0. 0 is not in this space, therefore this space is not complete. So far, all I've done is change the space that we're talking about, but use the normal notion of distance. In this problem, the space that we're talking about is going to stay fixed. It's always going to be the real numbers. What we're changing is the notion of distance. So the question is, for which of these notions of distance can we define a Cauchy sequence that does not converge to a point in the reals? Well, the reals don't have these holes like the rationals do, so we won't be able to emulate something like this purple example. So instead, we'll have to think of an example that's more like this one where we kind of focus on the endpoints. And you might be like, wait a minute, the reals don't have endpoints. The reals go from negative infinity to infinity. And that's entirely true. So what I need to do is come up with a Cauchy sequence of real numbers that, I don't know, maybe in quotes here, converge to infinity. All right, because infinity is not a real number. So if the limit of my Cauchy sequence is infinity, then that limit would not fall within this space, and therefore my space would not be complete. And so you might be like, wait, that's going to be really hard. How can my sequence possibly be Cauchy if the limit of my sequence is infinity? Well, I think the trick is to really understand what a Cauchy sequence is informally. Informally, a sequence is Cauchy if the terms of that sequence get arbitrarily close together. But remember, close together changes depending on our definition of distance. So with our standard notion of distance, there's no way this is going to work. Right? Maybe I choose epsilon to be equal to 1, sure. In order for my sequence to be Cauchy, there's some point in the sequence so that the distance between any two terms of the sequence after that point are within 1 of each other. But remember, the terms of the sequence are real numbers. So the capital Nth term in this sequence is a real number. And all subsequent numbers in the sequence must be within 1, if I choose epsilon to be equal to 1, of that real number. But the fact that any number within 1 of a real number, and when I say within, again, we're talking about this standard notion of distance, is itself a real number, means that that sequence will have to converge to a real number. So with our standard notion of distance, this is a complete metric space. But what if we consider this kind of strange notion of distance? The distance between two numbers is the absolute value of the difference in their arctangents. So if I asked you how far apart are 0 and 1, what you would do is you'd think back to your unit circle and you'd remember that the tangent of a given angle is just the slope of the line on your unit circle connecting the origin to that terminal point. What I'm saying is the tangent of pi over 4 is just equal to 1. All the arctangent is the inverse of this function defined from negative pi over 2 to positive pi over 2. So since the tangent of pi over 4 is equal to 1, the arctangent of 1 is equal to pi over 4. Similarly, because the tangent of a 0 angle is equal to 0, the arctangent of 0 is equal to 0. Therefore, the distance between 0 and 1 would be the absolute value of 0 minus pi over 4. In other words, pi over 4. How far apart are 0 and 1? They're pi over 4 apart. Think about the distance between two numbers is just the difference in the angles of the lines that have those slopes. In this strange world over here, 100 and 1000 are super close to each other. Why? Because if you drew a line with slope 100 and then you drew another line with slope 1000, the angles that define those lines would be damn near the same. Don't believe me? Here's a calculator. I'll put in the arctangent of 100. That's 1.56 give or take. And then I'll put in the arctangent of 1000. That's also 1.56 give or take. And 1000 is really, really close to 1 million. Don't believe me? Here's the arctangent of 1 million, also really close to those other numbers. If you're wondering what these numbers are, 1.57079 is very close to pi divided by 2. Oh yeah, that makes sense. On my unit circle, pi over 2 is right here. It corresponds with the right angle, which would be a vertical line, which would have an undefined slope. So the tangent of pi over 2 is undefined, and the tangent of numbers really, really close to pi over 2 get arbitrarily large. Well, we can take advantage of this fact that large numbers are really close to each other informally. All right, I can define a sequence. Let's keep it really simple. Let's let a sub n be equal to n. So if I index this thing starting from 1, my sequence is 1, 2, 3, 4, 5, etc. This is my Cauchy sequence. And you're like, no, this can't possibly be a Cauchy sequence. What if I choose epsilon to be equal to 0.1? How can you find a point in this sequence so all the numbers after that point are within 0.1 of each other? Every term in this sequence differs by 1. That's not quite true. The terms in this sequence differ by 1 according to our standard notion of distance. But if this is our notion of distance, these terms are getting really close. Right? If you choose epsilon to be equal to 0.1, for example, all I'd have to do is figure out what is the tangent of pi over 2 minus 0.1. Pulling out my calculator, it looks like that's a little bit less than 10. What that means is that the arctangent of 10 is roughly pi over 2 minus 0.1. But the limit, as n approaches infinity, of arctangent of n is equal to pi over 2. So since arctangent is strictly increasing, the arctangent of any number greater than 10 is going to be something between pi over 2 minus 0.1 and pi over 2. In other words, for any terms in my sequence after 10, the distance between those two terms will be less than 0.1. What I'm saying is this is a Cauchy sequence with this specific notion of distance. Every term in this sequence is clearly a real number, but the limit as n approaches infinity of this sequence is not a real number. This Cauchy sequence of real numbers has a limit that is not a real number. Therefore, under this metric space is not complete. I'm not going to prove that each of these are complete because I don't find the proof super enlightening, but in case you're curious how I think of these, I take it as a given that the reals under the standard notion of distance is a complete metric space. If you take that as like an axiom, then you can quickly prove that the reals under either of these notions of distance are also complete. The way I think about these is kind of by contradiction. Assume this is incomplete. Then I have a Cauchy sequence of numbers under this notion of distance whose limit is not in this space. See if you can show that that would imply that the reals under this notion of distance would also be incomplete. We know this is complete, therefore we know we were wrong to assume that this was incomplete. Same logic for D. I think E is a little bit more interesting, especially if you're not familiar with this discrete metric. The idea here is that distance between any 2 points is equal to 1 unless those 2 points happen to be the exact same number. If you haven't seen this, convince yourself that it satisfies all these criteria for being a metric, and then think about how you could show that it's complete. Well, what would a Cauchy sequence look like under this notion of distance? Maybe you choose epsilon to be equal to 1/2. That means there's a point in this sequence where all the numbers after that point are within 1/2 of each other. But the distance between points in that sequence are either 0 or 1, so the only way they're less than 1/2 is if they're equal to 0. But if they're equal to 0, that means they're the same number. So there's some point in the sequence after which the sequence becomes constant. But if the sequence becomes constant, then the limit of that sequence is that constant value. We know that constant value is a real number, therefore the limit must be a real number, therefore this space must be complete.